Yeah, good morning, everybody. Um, Today we'll be looking at second law of thermodynamics. This is Jude Come. We know that in thermodynamics, there are basically four laws of thermodynamics, of which the zeroth law of thermodynamics was not included in our discussion. Now, here we have the zeroth law, the first law, and the second law. Now, the zeroth law of thermodynamics basically introduces a new property the system, known as the temperature of the system. It tells us that when three bodies are mutually interacting with each other, gets to a point where they become thermal, when they become in thermal equilibrium. Now, the next one, we have the first law of thermodynamics. It talks about the conservation of energy. It talks about the conservation of energy, that energy can either be created, not destroyed, but can be converted from one form to another. Then it introduces a new property of the system known as the internal energy. But in this case now, we'll be looking at the zeroth law of thermodynamics, the second law of thermodynamics. Now, the second law of thermodynamics virtually introduces the direction of flow of a process, direction of flow of a heating process. Now, what do we mean by that? It tells you the direction of time, the direction of flow of a spontaneous process. And also, it tells us why that energy that is converted into work, that's energy that is converted into work is not what's possible. That we cannot have all the energy given to a system converted into work. And also give us the exact feasibility of a process. Now, this law introduces a new property known as the entropy and the free energy of a system. Now, basically, the second law of thermodynamics was stated in three forms: the Clausius statement, the Kelvin statement, and the entropy statement. Now, the Clausius statement talks about heat flow from a cold body to a hot body, that it is not possible to have heat flowing from a cold body to a hot body without an intervention of an external energy. So for it to flow from a cold body to a hot body, then there must be an external force applied to that system. Now, the Kelvin statement basically talks that it is impossible for heat coming from a hot body to be converted into work without transferring part of the heat to a cold body. Now, this hot body and cold body, we can also call them reservoirs. We can call them reservoirs. So, heat flowing from a hot body converted into work, all the heat flowing from the hot body converted into work without going into the cold body, it is what? Impossible. An example of this statement is the internal combustion engine. That is, it's impossible for us to have an external combustion engine to convert all its heat to work. Now, the last one says the entropy statement says that a spontaneous process is always accompanied by an increase in entropy of the universe. What is entropy? Entropy basically means the rate of disorder of a system. That for every spontaneous process, for every process happening in one direction, the entropy of the system basically increases. Now let's continue. Now the next statement there, we said that we have other statements. We have other statements. We have other statement of the second law of thermodynamics. We have that all spontaneous processes are irreversible. That means if we're having a spontaneous process and the entropy is basically increasing, it is an irreversible process. And yeah, we have it is impossible. It is not possible to construct a machine that is functioning in a circle, which converts it completely into equivalent amount of work. It's the same thing as a Kelvin statement, which we stated earlier. Now let's look at heat engines. Let's look at heat engines. Now, heat engines convert heat to work. So we have several types of heat engines. We have the internal combustion engines, particularly. Now, there are several types of heat engine, and they are characterized by the following. First one, they all receive heat from a high temperature source, also known as the hot reservoir. This is the high temperature source from this diagram here. Now, they convert part of the heat to work. This is a conversion process. They reject the remaining waste heat to a low temperature sink known as the low heat reservoir. And this is where we're having it here. And they operate in a circle. That means they operate in a cyclic process. Now, for heat engine, the heat is what? The heat that is converted into work in the circle is the work done in this cyclic process is little compared to the amount of heat given to the word circle. So we have the hot reservoir source or the high temperature source and the low temperature sink. So that we have that the net heat, the net work or the net energy, which is converted to work, simply is the sum of the input heat from the hot reservoir source or the high temperature source plus the output heat from the low temperature sink. Now, basically, to calculate the efficiency, you should take note of this formula. To calculate the efficiency, it is defined as the benefits divided by cost. That means the work output, the output work divided by the input energy. Now, we basically know that the output energy is taken as the input heat minus the uh output heat. Now, when we sum it here, we have that here will give us Q in, let me represent it as QI minus Q out, that is Q naught, divided by QI. Now here, we see that they are both having common denominators such that we have that if QI and QI will subtract each other, so we have 1 minus Q out, divided by Q in. So here we're having that our efficiency is basically lesser than 100%. It's basically lesser than 100%. Yeah, they say for an ordinary spark ignition automobile engine, the total efficiency is 20%. For a diesel engine, it is 30%. And for a power plant, it is 40%. So basically, the efficiency of heat engines are basically lesser than 100%. So let's continue. Oh, yeah. Now let's look at the second law, the Kelvin-Planck statements. Now they said it is impossible for any device that operates in a circle to receive heat from a single reservoir and produce a net amount of heat. It simply means that no heat engine has a thermal efficiency of 100%. Yeah, we can see that no engine or no device can operate in a circle, receiving heat from an hot reservoir and then converting all the heat to work. such that we now have that heat engine, it is impossible to have its efficiency as 100%. So let's look at the next one, the refrigerators and heat pumps. Now, basically, heat pumps works under the cautious statement that heat flowing from a cold region and converting it into converting it flowing from a cold region to a hot region. That it is impossible to have heat flowing from a cold region to a hot region. That is a cautious statement. Like I said, in nature, it basically flows from high temperature regions to low temperature regions. But for refrigerators and heat pumps, it is the reverse process. Heat flows from a cold temperature region to a high temperature region. And for this to happen, we say that an external energy is required. An external energy is required for this to happen. So we say refrigerators are cyclic devices and the working fluids in these circles are called refrigerants. Now, heat pump transfer heat from a low temperature medium to a high temperature one. Refrigerators and heat pumps actually are the essential device. They differ in their objective. Refrigerator is to maintain the refrigerated space at a low temperature. On the other hand, the heat pumps absorbs the heat from a low temperature source and supplies the heat to a warmer temperature medium. So this is the working cycle of a refrigerator and a heat pump. Now, this is the warm environment. This is the cold refrigerated space. This arrow shows that heat is transferred from the cold region and to the warm environment. This arrow tells us that work is done on the system here to achieve heat transfer from a cold region to a warm region. Same thing goes for the heat pump. Now, for heat pumps and refrigerators, we don't use the word efficiency, we use the word coefficient of performance. Now, the performance of a refrigerator and heat pump is expressed in terms of coefficient of performance, and it's defined as benefits divided by cost, meaning that the heat in the low temperature region divided by the work done on the system. This is the coefficient of performance for a refrigerator, while the coefficient of performance for a heat pump is the heat in the hot region divided by the work done on the system. Now, we can see that the coefficient of performance for a heat pump is greater than the coefficient of performance for a refrigerator by 1. So we have the efficiency rating, EER, is given as 3.412 coefficient of performance for a refrigerator. Now let's look at the cautious statements. Since we've explained the concept of refrigerator and heat pump, the cautious statements say that it is impossible to construct a device that operates in a circle and produces no effect other than the transfer of heat from a low temperature body to a high temperature body. So we should take note of that. From a low temperature body to a high temperature body, that is impossible to produce a device without the effect of an external energy. Without the effect of an external energy, we have impossibility there. It's impossible to make a machine of sorts. So in other words, a refrigerator will not operate unless its compressor is driven by an external power source. Now, basically, if we observe the Kelvin Planck statement and the cautious statement, all talks about impossibility, that it is impossible. It is impossible. The first one says that it is impossible to have heat coming from a hot reservoir, then converting all the heat to work. While the cautious statement says it's impossible to construct a device working in a circle that can transfer heat from a low temperature region to a high temperature region without the effect of an external energy